Chapter 5.1 Irrigation Management. Although moringa is a drought-tolerant tree, in commercial and production environments, supplemental irrigation is arguably the most important and most overlooked aspect of growing moringa. Nursery and greenhouse growers depend heavily on the ability to irrigate daily during landscape production cycles. Florida receives, on average, 50 to 60 inches of rainfall, or enough to maintain any landscape. Unfortunately, rainfall is not distributed evenly enough to actually eliminate the dependence on supplemental irrigation. As a result, the timing, frequency, and amount of supplemental irrigation is often determined without proper knowledge or understanding of moringa's water needs. The following section is designed to help everyone growing moringa. A. Understand the principles of water conservation. B. Determine when moringa trees needs water. And C. Provide tools that can be shared with growers following installation on the proper ways to maintain a healthy, vigorous, and productive moringa trees. Irrigation should be managed closely. Water is very valuable, and adding it to the soil for the purpose of supplying the appropriate moisture for optimal growth is a modern luxury. Irrigation also provides a means for nutrients to move from the soil to each moringa tree and is used for salt leaching, chemigation, system flushing, seed germination, and climate modification. Providing an adequate amount of water to satisfy the moringa tree's needs at the correct time is the key to resource conservation, reduced pollutant loading, and optimum growth. Conversely, over or under irrigating nursery or orchard trees will lay the foundation for a litany of consequences, including growth decline and disease problems, plant death, leaching and runoff of nutrients, amendments, pesticides, and wasted time and money. Irrigation management, knowing when and how much to irrigate, is the cornerstone of water conservation and reduced soil movement. Proper irrigation scheduling should consider plant water requirements, recent rainfall, recent temperature extremes, and soil moisture. Under ideal conditions, the water required for moringa irrigation and maintenance is equal to the water lost or used during the entire tree's cycle of growth. Water loss is attributed to soil evaporation and plant transpiration. Typically, both processes are combined and called evapotranspiration, ET. A moringa tree's water requirements, ET, vary with its growth cycle and climatic conditions throughout the year. Moringa trees use more water during seed, flower, fruit production and may not require irrigation in dormancy. During the colder months, most moringa trees are not actively growing in the USA. It just gets too cold and thus use less soil moisture. Excess irrigation can waste our water supply, cause off-site damage, cause pollution, and have direct economic impacts. Over-irrigation causes water to run off and possibly flood adjacent properties, or the water percolates below root systems and provides no benefits to the moringa trees or surrounding areas. Excess water can carry away nutrients or other minerals that could murky nearby water resources. The wasteful use of water increases both the user's water bill and fuel costs associated with pumping the water out of the well or through the lines and pipes. There are several ways to prevent excess irrigation. Visual observations of runoff or puddles are simple indications. A system's timer clock controller can be adjusted to meet each moringa tree's water requirements. Flow meters can be used to determine how much water is applied and when to turn off the irrigation system. A tensiometer or electronic moisture sensor can be placed below the root zone to determine the status of the wetted front and when to tum off the irrigation system. Rain gauges, cans, or other containers can be used to measure how much water has been applied so that you don't water while it's raining. Link your controllers to an application on your phone to also start or stop the watering at any time. Watering frequency. Currently, there are several methods that can be used to determine when and how much irrigation to apply in a landscape setting. For example, actual or potential ET values, soil moisture sensors, and automated ET controllers represent the latest technology available for use in residential and/or the commercial setting. Ideally, irrigation scheduling should be based on site-specific conditions which dictate soil moisture. Tools such as soil tensiometers or other soil moisture probes provide the ability to determine site-specific conditions, yet these tools are often impractical and/or unaffordable in many cases. In situations where the use of the latest technology isn't feasible, other acceptable methods, such as potential evapotranspiration, ETP, can be utilized. Current estimated ETP rates are available for specific regions throughout Florida. Figure 401 lists average ETP levels in 2 regions of Florida, and based on the ETP findings for turfgrass, we can also gather some ideas of how much water will be needed to maintain healthy moringa trees. If we know that ETP accounts for half of the water being irrigated, 2x the number in figure 4.1 for an accurate watering amount per day. The numbers are based on a diagonal line running from north of Tampa to south of Daytona Beach, dictating the northern and southern part of the state. ETP values should be used only as a general guideline for irrigation scheduling and for monthly timer controller adjustments when local site-specific information is not available. Figure 5.1, potential evapotranspiration, ETP, levels for 2 regions of Florida by University of Florida, IFAS. Watering amount. An irrigation event should apply enough water to penetrate the average depth of the root system of moringa trees in the ground or to the bottom of the container for moringa trees in containers. Even for deep-rooted moringa trees, water only needs to penetrate underlying moist soil. How much water that is will depend on the nature of the soil. Inches are often used when discussing how much water to apply. Application of an inch of water means enough water applied evenly over the area begin irrigated so that if it were all on top of the area at one time, it would measure 1 inch deep. An inch of water applied to sandy soils would penetrate about 12 inches deep, while an inch of water applied to a loam soil or soil mix will only penetrate about 6 inches. Using this information, a pot 6 inches deep should have approximately 1 to an inch of water applied, and a plant with an average root depth of a foot should have an inch of water applied. However, to prevent over-irrigation and the leaching of fertilizers and amendments, and to promote root development for drought conditions, research suggests that, in general, no more than 1/2 to 3/4 inch of water should be applied for a single irrigation event. Another basic method used by moringa growers is to assume that on average 1 inch of water wets the top 12 inches of a sandy soil. Because most roots grow in the topmost 6 inches of soil, 1/2 to 3/4 inch is needed for replenishment every 2 to 3 days during periods of active growth, and every 10 to 14 days during less active growth periods. This water can come from rainfall or be provided by the irrigation system. In less sandy soils, 1 inch of rain could only penetrate 3 to 6 inches of soil. In a rainfall event, when measuring the amount of water that already fell on your moringa trees, trying to figure out how much you need to irrigate, calculate the remaining water demands, if any, by using the surface area that you are trying to water, keeping in mind the ETP calculations for your region as well. When calculating the waterfall depth, for example, in an open milk jug after a rain is not actually accurate in true depth to rainfall ratio because the opening on the top of the jug is a much smaller area than the rest of the jug. Once it's filled with water, there is a slight bulge in the center of the jug. That's why most rain gauges are conical in shape, and to get a more accurate reading, if you look closely at the graduations, you'll see the measurements get progressively closer together at the top because the surface area is progressively larger as the gauge fills up. Rainfall in inches is described as water that falls on any area measured in depth, typically in inches or millimeters. 25 millimeters equals 1 inch. 1 inch of rain can also be calculated with a 1 foot square pan, a 4-inch can, and a 4-foot tub. They would all reach a depth of 1 inch at the same time. 1 inch deep can be calculated for any size area with a simple formula. How much water is needed to cover 1 square foot 1 inch deep? If 1 gallon is 231 cubic inches and 1 square foot is 144 square inches, the volume of water, bar 12x 12x1, bar 144 cubic inches, 144, 231, 0.37 gallon, mar 79 fluid ounces, or 2.35 liters of water. 1 inch of rainfall can be calculated as 4.7 gallons of water per square yard, or 22,750 gallons of water per acre. 1 gallon is 231 cubic inches, so an area of 231 square inches, roughly 23 inches x 10 inches x 1 inch, would hold 1 gallon of water at 1 inch deep. Rain shutoff devices, required by law, and rain gauges should be placed in open areas to assure accurate readings. Flow meters should have a straight enough run of pipe both downstream and upstream to prevent turbulence and bad readings. Tensiometers and other irrigation management tools should be installed in representative locations and should be maintained to help make good irrigation management decisions. Although irrigation management is a complex process, it can be reduced to a simple checkbook or water balance process. The irrigation amount should consist of the difference between the moringa tree's water use and effective rainfall, i.e., rainfall stored in a moringa tree root zone for its own use. Another way to determine irrigation requirements is to determine the soil moisture deficit that needs to be replaced. Irrigation timing. When mechanical, electronic devices are not available for irrigation management, the following visual indicators can be used as guidelines to determine the need for irrigation. Moringa leaves have a dull yellow-gray coloring. Leaves are curling and folded or have burned edges. Soil samples from the root zone are dry and crumbly. Indicator landscape plants, such as mimosa, perennial peanut, and longevity spinach, have drooping leaves. When possible, the timing of an irrigation event should be planned to increase irrigation efficiency by reducing evaporative losses due to climatic conditions. For example, high temperature, low humidity, windy conditions, and by maintaining high irrigation uniformity. These conditions normally occur in the early morning hours. On a typical summer afternoon, it would not be unusual to lose 40% to 50% of the water being discharged through an overhead sprinkler to wind or high evaporative loss. However, it is often necessary to water several times a day after planting new materials, seeds, and cuttings in the summer to assure successful establishment. These more frequent applications should be carefully monitored and reduced as soon as possible. Several irrigation management techniques help to improve a plant's health and reduce water use. Delayed irrigation and deficit irrigation promote root development and provide a level of drought tolerance. Delayed irrigation promotes deeper root development by postponing irrigation until wilt is observed. Deficit irrigation calls for managing irrigation quantities so that there is always soil storage to take advantage of any possible rainfall. Regardless of the methods or tools you utilize when determining irrigation applications, the point is to be consistent and use some method other than setting an automated irrigation timer and never adjusting the run times. For more information, see Grow Moringa blog on tips for maintaining moringa trees during drought. See bibliography. Application uniformity. Moringa seedlings should all be soaked evenly using the wicking method, watering and fertilizing from below, not spraying water on the sensitive leaves while growing in a greenhouse. Moringa trees in the ground and in containers need more irrigation. Uniformity and application is a critical function of irrigation system efficiency, as it indicates how uniformly water is distributed over a wetted area. Greater application uniformities occur when spacing is adequate and sprinkler nozzles are matched. Poor application uniformity leads to localized over-irrigation or under-irrigation. Lack of application uniformity can lead to holes in watering patterns, yellowing, and stressed moringa trees, which will bring even more pests into the environment. In most cases, uniformity problems can be easily corrected. Once uniformity problems have been addressed, savings in electricity, fuel, and watering costs can be realized. Poor uniformity in overhead sprinkler systems can be due to numerous factors, such as A. Improper pipe diameters, B. Improper operation pressure, C. Improper sprinkler heads and nozzles, D. Inadequate sprinkler overlap, E. Wind, F. Changes in system components with time, such as pump efficiency, pressure regulation, or nozzle size, and G. Nozzle clogging. The only way to know for sure how even the application and how much water an irrigation system is putting out is to measure it. There are several methods for determining irrigation uniformity. The most common method is referred to as the trash can test. The catch can test can be conducted by placing cups or jars or other straight-sided containers evenly around sprinklers to catch and measure irrigation. The system is turned on for a fixed amount of time, and the water collected in each container is measured and recorded. If irrigation is uniform, the amount of water should be close to the same in each container. For sprinkler systems, 70% to 80% is considered good uniformity, and anything above 80% is excellent. Application efficiency. Application efficiency is another form of irrigation system efficiency. It indicates how much of the applied water is stored in a plant's root zone. For sprinkler systems, application efficiencies typically range between 70 and 85%. Application efficiency and emission uniformity. Measurements are used to determine micro-irrigation system efficiencies. In general, microsystems with emission uniformities of 90% or greater are considered excellent. 90 to 80% are good, 80 to 70% fair, and below 70% poor. For more information, see Grow Moringa Farms' publication on field evaluation of micro-irrigation water application uniformity. See bibliography. The different system efficiencies determine how well a system can perform, but since they do not include irrigation management, they do not show how well the system is operating. To determine the overall irrigation efficiency, divide the total water used for reasonable and beneficial use, such as evapotranspiration, salt leaching, and establishment, by the total water provided and multiply by 100 to create a percentage. The higher the value, the more efficient the irrigation. In some areas of the state, the water management districts or other local agencies may provide mobile irrigation lab (MIL) services. These services will evaluate a system and make recommendations to improve system efficiency. Contact your local water management district for more information about these services in your area. Irrigation BMPs, the fundamental best management practices for irrigation management are: irrigation rates should not exceed the maximum ability of the soil to absorb and hold the water applied in any one application. Irrigation quantities should not be larger than the available moisture storage in the root zone. Never over-irrigate. Use properly calibrated flow meters, soil moisture sensing devices, rain gauges, and the visual observation of irrigation runoff or puddles to manage irrigation. When possible, the irrigation schedule should coincide with other cultural practices, such as the application of fertilizer, herbicides, or other organic soil amendments. When fertilizing, other than when watering restrictions apply, irrigate with 1/4 inch following fertilization to avoid the loss of nitrogen and increase uptake efficiency. If water restrictions apply, you may irrigate as you are allowed, but more than 1-2 inch of water may cause some loss in efficiency of your application, and nitrogen could be leached past the root zone. Proper cultural practices should be employed to promote healthy, deep root development and reduce irrigation requirements. Irrigation controllers, timers, should be reset seasonally to account for moringa tree growth requirements and local climatic conditions. Where applicable, distribution, emission, and application uniformities should be tested annually. Chapter 5.2, Irrigation System Design Principles. Florida has 67 counties, each with different regulations and requirements concerning licensing, design, and approval of an irrigation system. The following section is helpful general information, but for more answers about where to start with your property, join one of the live webinars inside the members area and ask some questions. If you'd like one-on-one consultation from a trained member, we can schedule a call back with you. Irrigation system design is a complex issue and should be handled by trained professionals. These professionals should use existing standards and criteria, as well as the manufacturer's recommendations to design the most appropriate system for a location. A list of sources for current standards and criteria can be found at the end of this chapter. Remember that in many communities, construction, design documents, and permits require the signature and seal of a registered design professional. An irrigation system needs to be designed to meet a site's peak water requirements. However, the system should also have enough flexibility to adapt to various water demands and local restrictions, and allow for operating modifications to meet seasonal irrigation changes. To prevent irrigation runoff, a system's application rate must not exceed the ability of the soil to absorb and retain the water applied during any one application. The system operating pressure must not exceed the source pressure. The design operating pressure should account for low pressure during periods of high use, i.e. mornings, and for project build-out or expansion. Since moringa trees need different irrigation times for each season, irrigation systems designed to service them throughout the year is crucial to meeting their individual water needs. The irrigation design should also account for the extra water needed periodically to leach salt buildups that accumulate due to poor irrigation water quality. An irrigation system consists of three main components. 1. Water supply, water source, pump, filters, and valves. 2. Water conveyance, mainline, manifold, lateral, and spaghetti tubes. 3. Distribution device, impact sprinkler, oscillating sprinkler, rotary sprinkler, spray, or drip emitter. Distribution devices and pipe sizes should be designed for optimum uniform coverage. Distribution equipment, sprinklers, rotors, and micro-irrigation devices in each zone must have the same precipitation rate. The proper selection, design, and installation of these components optimizes their use and decreases any off-site impacts. The design must also account for different site characteristics and topographies. To provide peak water use demands and have enough flexibility to reduce supply for different demand requirements, irrigation systems need to be designed with varying control devices, rain shutoff devices, and backflow prevention. Backflow prevention devices required by law are installed in irrigation systems to prevent water in the system from flowing back into the water supply. Obviously, this becomes critical if fertilizers or pesticides are injected into the irrigation system. They also release pressure from the tubes, which keeps your system functioning longer. Figure 5.2 irrigation spacing. Water conveyance systems should be designed with thrust blocks and air release valves to prevent system damage. Equipment with check valves must be used in low areas to prevent low head drainage. The water conveyance pipelines should provide the system with the appropriate pressure required for maximum irrigation uniformity, and the distribution devices should be designed for optimum uniform coverage. In addition, the distribution system should not include the irrigation of non-planted areas, such as driveways, parking lots, roads, sidewalks, underneath roof overhangs, and natural buffer zones. Figure 5.3 square spacing. To ensure optimum uniformity, permanent irrigation sprinklers, spray jets, and other distribution devices should be spaced according to the manufacturer's recommendations. Typically, this spacing is based on average wind conditions during irrigation. In the absence of this information, guidelines such as Figure 5.2 can be used. For variable wind directions, the triangular spacing shown in Figure 5.4 tends to be more uniform than the square spacing shown in Figure 5.3. Figure 5-4, triangular spacing. Practical experience may suggest closer spacing than the guidelines. However, spacing should not exceed the percentages in Figure 5.2. After the system is constructed and operating, periodic trash can uniformity tests should be performed to assure system efficiency. Chapter 5.3, Micro-irrigation for moringa trees. Irrigation systems operate most efficiently with moringa trees if they don't wet the foliage or leaves, especially moringa sprouts in a greenhouse. In that case, use the wicking method to water from below using trays, sprouting moringa trees in pellet pots. Moringa leaves have a natural wax coating that repels water and dirt. They are called hydrophobic in nature, and the leaves don't even use water applied to the foliage for metabolism. The most efficient and effective watering method currently available for landscape purposes and large container plant production is micro-irrigation, which includes both drip and trickle irrigation. Micro-irrigation supplies small quantities of water directly to the mulch and soil through plastic tubing on or below the ground surface at or close to the root system of the plant. Low pressure emitters, that is, nozzles that drip, spray, or sprinkle, are attached to small plastic tubing and slowly release water into the soil around a plant. Wetting only the root zone saves water because less evaporates. Because of the low rate and proximity to the root system, micro-irrigation can be applied at any time of the day. The selection of emitter types, i.e. drip emitters or spray jets, in each location is important to assure adequate coverage. With drip emitters, water moves laterally in sand only 10 to 12 inches from the emitter. Drip emitters are ideal when such precision is desirable in containers or for narrow strip plantings, such as along hedgerows. Because drip emitters are sometimes placed under mulch or buried in the soil, clogging may occur that is difficult to detect. In addition to clogging, it is hard to know whether the system is irrigating excessively due to a hole in the tubing or some other problem, because the action of drip emitters is not readily apparent. Regular visual inspection is required to make sure that the drip emitters and the overall system are functioning properly. In some cases, spray jets, either micro sprayers or micro sprinklers, are more desirable than drip emitters because spray jets can cover areas 3 to 20 feet in diameter. Fewer emitters are needed. Not only is their action visible, but the greater flow rate of water through spray jets, 10 to 20 gallons per hour versus the drip emitters 0.25 to 2 gallons per hour, also makes them less susceptible to clogging. Microsprayers create a fan-shaped distribution of fine water droplets. These fan jets perform well when used for directional spray and confined area applications. Some manufacturers have added spinner devices to create a sprinkler effect. These micro sprinklers have more uniform water distribution than fan jets and can provide excellent coverage. Poor water quality may also clog emitters, regardless of the style. Clogging can be reduced if filters are installed on the system. Filtering well water and surface water is strongly recommended. The safest and easiest way to maintain the emitters in a micro irrigation system is to keep a small supply of clean backups on hand for quick replacement. One of the best filtration systems is a simple settling tank. If you get a large enough tank and your water source is stored there, before going into the lines, the settlement will drop to the bottom. Only pump from the surface water and dump the sludge that forms on the bottom with a drainage plug. For more information, see the Grow Moringa blog, Micro Irrigation for Moringa Trees, and Procedures for Micro Irrigation Systems. See Bibliography. Chapter 5.4, Irrigation System Installation. Qualified professionals that are appropriately licensed, bonded, and insured should handle irrigation system design and installation. These individuals must follow the designer's plans and use existing standards and criteria, such as those available from the American Society of Agricultural Engineers, ASAE, Florida Irrigation Society, FIS, Irrigation Association, USDA Natural Resources Conservation Service, NRCS, or from the manufacturer's recommendations. The designer must approve any changes to the system prior to installation. To prevent system failures, waste, and property damage, construction materials must meet appropriate quality standards, such as ASAE, American Society of Civil Engineers, ACE, or American Society of Testing Materials, ASTM. All underground cables, pipes, and other obstacles must be identified and their locations flagged before construction. Acceptable safety practices must be followed during construction. At the end of construction, the owner should receive a copy of the as-built plans, operating manuals, warranties, and written instruction on how to change the irrigation system, timers, clocks, controllers. The site must be cleaned of all construction materials before the job is complete. Irrigation system maintenance. Proper maintenance extends the life of an irrigation system and helps it to perform optimally. Maintenance begins with a visual observation of the system and the moringa trees. Perform weekly checks for leaks, broken, cracked lines, proper rotation, and damaged sprinkler heads. Also, check for obstacles that may interfere with irrigation uniformity. Check the moringa tree leaves for brown spots, unnaturally yellowing. Certain types of weeds on the ground indicate deficiencies. Notice if there are any suspicious mushrooms, fungal spots, sogginess, and algae are indicators of problems. Damaged, defective systems should be repaired as soon as possible, preferably before the next scheduled irrigation. Replacement parts should always have the same characteristics as the original components, i.e., discharge pressure relationship, jet size, colors, etc. Otherwise, the replacement might cause more harm than the bad component. Implement a preventive maintenance program to replace worn components before they cause fertilizer, chemical, and water waste. Common irrigation efficiency problems include leaks, sprinkler head plugging, poor irrigation uniformity caused by nozzle wear, and poor system pressure. Some problems, such as repairing leaks and replacing nozzles, can be fixed at a minimal cost, while others, such as poor system design, might be very costly. However, problems need to be corrected as soon as possible to prevent the leaching of fertilizers or chemicals and/or wasting water. In the long term, investments made to improve the irrigation system pay off in the form of reduced fertilizer, chemical cost, and water bills. Irrigation system errors. Improper irrigation system design, installation, or maintenance results in moringa trees being overwatered or underwatered if areas are not zoned separately. Application or runoff water to non-target areas, such as towards a building, the street, or sidewalk. Objects interfering with spray patterns, resulting in poor distribution uniformity. Wasted water from undetected broken pipes or broken heads. Chapter 5.4, Permitting and Regulations. In Florida, there is an ever-increasing problem of decreasing usable water supply. Florida experiences periods of high rainfall in the summer. The natural environment once retained much of the summer rainfall. However, with increased development, drainage, asphalt, and concrete, natural retention of water has been greatly reduced. Because periods of rainfall are irregular, Floridians must depend on supplemental irrigation to produce and manage ornamental plants. But the groundwater from the aquifers are under more pressure now than ever, causing sinkholes. Many agencies have jurisdiction over irrigation projects before, during, and after construction. For example, Florida's 5 water management districts, Florida Department of Health, Florida Department of Environmental Protection, and local governments will likely require permits. To prevent potential fines, it is important to follow all regulatory requirements and secure the appropriate permits. These suggestions are for growers seeking to irrigate more than an acre of land. If you are in your backyard getting your operation started, use these guidelines to construct the most efficient system possible with the knowledge provided. You are maybe able to do it yourself, or at least consult with a trained member to help. There are water use permits in many counties. Check with your municipality before turning your irrigation system on. The water management districts have special drought water shortage restrictions that govern the amount and timing of irrigation. Collecting rainwater could be used for irrigation. It is important to know the restrictions for a site and to set controllers to those conditions. Since water shortage restrictions change with the severity of a drought, it is important to be aware of and to abide by current restrictions. If a site's irrigation system cannot be adjusted to meet the restrictions, the system should be upgraded as soon as possible. But in the interim, there are methods to obtain variances. These variances need to be obtained by the city in writing before irrigating. The following permitting and regulatory guidelines should be followed for all irrigation projects. Contact local and state regulatory agencies, such as the county, city, Florida Department of Environmental Protection, water management districts, and health department to determine current irrigation regulations and criteria. Obtain all permits before construction. Abide by all permit conditions and current water restrictions when operating the irrigation system. Obtain any desired regulatory variances before irrigating. The use of irrigation best management practices, BMPs, promotes proper irrigation system design, construction, and management. This leads to reduced water use, the protection of aquatic resources, better plant development, economic savings to the end user, and efficient fertilizer use. Irrigation standards. The following publications contain current irrigation standards. Contact information can be found in the references Chapter 10. Asabi Standards, 2006. Standards, engineering practices, and data developed and adopted by the American Society of Agricultural and Biological Engineers. Florida Building Code Plumbing Volume, Appendix F, Southern Building Code Congress International, Inc. Standards and specifications for turf and landscape irrigation systems by the Florida Irrigation Society. National Engineering Handbook by the U.S. Department of Agriculture, Natural Resources Conservation Service. Chapter 5.6 Irrigation Parts. Smart water management is the only way to healthy, happy plants and trees. Among the many methods and tools available to manage water wisely, drip irrigation remains one of the most popular and effective. Also referred to as low volume or micro irrigation, drip systems are ideal for virtually all landscaping applications. Drip irrigation can use PVC pipe as the main lines, then go into polyethylene tubing following the drip emitters. PVC systems are usually reserved for larger scale applications like farming, while polyethylene tubing is the choice for home gardening. We'll be covering both PVC and polyethylene in this section. The examples below describe irrigation systems for moringa seedlings and sprouting moringa trees in an intensive or fedge condition. The poly tubing, for example, is located on the ground, but my best experience with growing moringa in an orchard setting is to elevate the one thick poly tubing 3-4 above the ground, held up with metal stakes or the trees, and connect a 1-hour micro tube with a drip emitter. The one pictured below is wrapped up to avoid damage during harvest, but it was unwound and staked back on the ground in the middle of both trees. This moringa tree is in between two citrus trees. Components of a drip system. There are 3 primary components to any drip system: tubing, fittings to connect tubing, and the emitters that deliver water. For larger systems further from the water source, PVC can be used as the main line connecting to the tubing. PVC. When it comes to selecting PVC irrigation pipe, both Schedule 40 and Schedule 80 pipe are common types of irrigation PVC pipes. They handle pressure roughly the same, so you won't have to worry about more frequent breaks if you opt for Schedule 40. Schedule 80 pipe has thicker walls and is subsequently more structurally sound, so you might want to go with Schedule 80 pipe if you are building an above-ground system. PVC is typically buried saint. Regardless of the type of PVC pipe you choose, it is important to expose the pipe to as little sunlight as possible. While some PVC types have more resistance to sunlight than others, any PVC pipe that is exposed to sunlight for long periods of time will quickly become brittle. To sunproof your irrigation system, there are several options. 3-4 coats of exterior latex paint offers enough sunlight protection. You can also use foam pipe insulation. Below ground systems do not need sunlight protection. Finally, water pressure is not a huge issue when it comes to laterals. Most pressure surges in irrigation systems occur in the main line. Subsequently, you will only need PVC pipe that has a PSI rating equal to the pressure in your system. Placement and fittings. If you opt for a below ground system, make sure that you bury the pipe at least 10 deep. PVC pipe is brittle, and a strong hit from a shovel can easily crack or break it. Additionally, PVC pipe that is not buried deep enough can float to the top of the soil during the winter. It is also a good idea to put foam pipe insulation on both above ground and below ground systems. This insulation can protect pipe from sunlight in above ground systems and protects against freezing during the winter. If you choose to use PVC pipe for your irrigation laterals, make sure to use pipe that is at least 3x4 thick. 1-2 inch laterals clog very easily. If you choose to use fittings, most common PVC fitting types work fine. Socket fittings with primer cement hold securely, and threaded fittings, both metal and PVC, do the same. First, apply the purple primer to the PVC you are connecting, then add a layer of cement. You can also use push fittings, which use flexible seals and teeth to lock it into place. If you use push fittings, make sure to choose fittings with high-quality seals. Tubing. Plastic tubing is the backbone of any drip system. The black poly tube is typically manufactured from top-quality UV-resistant polyethylene. This contractor-grade tubing is designed to help eliminate pipe failures due to UV light damage and environmental stress cracking. In a typical home garden setup, 1-2 poly tubing is used as the main line connected to the water source. Then in the rows, place 1-4 tubing to which emitters are connected. If your system is a bit larger, start with PVC near the water source. Bury it to reach the plants. Then use the 1-2-1-4 poly tube down the rows. Worried about kinks, cracking, or deterioration? If you require a sharp bend in your line, cut the tubing and use an elbow fitting. Fittings. Tubing and emitters alone will deliver water, but without fittings, a drip system is little more than a leaky hose. Fittings allow for an irrigation system of greater complexity and efficiency. Fittings that connect the PVC to the poly tube are simple. Using the primer and cement, secure a male threaded fitting over the PVC pipe. Then using a male-female adapter, screw onto the PVC. Then connect to the poly tube and seal it with a metal clamp. Emitters. Although drip is usually how it is referred to low-volume micro-irrigation, there are several emitter types. There are different emitters depending on a plant's needs, the soil type, or the landscape design. Emitters for trees should be located to provide balanced root development. While a single, small-capacity emitter may be sufficient during the early years of plant development, a higher flow rate will be needed as the tree matures. This large flow should be divided between several emitters, spaced around the trunk within the canopy drip line. The drip line is simply the line marking the extent of the tree canopy coverage on the ground surface. Pro tip: For garden features, locations with a 5-foot elevation difference from the main supply line of the drip system, pressure compensating PC emitters are recommended. Their internal design will guard against any variations in flow caused by the change in pressure. Drip emitters, the most precise option, delivering water directly to the soil at the root zone at very slow rates. Drip emitters are suited to most vegetable gardens, trees, hanging baskets, etc. Because of the low discharge rate, the watering cycle is usually longer. The external emitters pictured below puncture the poly tubing and are called point source emitters. Some poly tubing already has a hole with an internal emitter, but unless you plant a tree in the exact spot of the pre-made hole, you'll be wasting water. Microsprays are not as used in moringa irrigation because the leaves don't like to be wet all the time. They do better dry while using drip on the root zone. Even in a greenhouse, moringa trees do better with the wicking method and watering from below with a tray. Bubblers, most often used for more established trees. With their higher discharge rates, they have short watering cycles. Because bubblers can operate at high pressures, they are particularly useful for conversion from conventional sprinkler to low volume systems. Because watering times are typically very long, timers are an especially good idea for drip systems. After several hours, it's easy to get distracted and forget to turn the system off. In addition to emitters, tubing, and a timer, you'll need a vacuum breaker installed to keep contaminated water from being siphoned into your home's water supply. You'll also want to include a filter to prevent clogging from sediment and other particles. And unless you have very low water pressure, a pressure regulator is often another necessary addition. Drip systems perform best with a 20 to 25 psi supply pressure. Design tips. Before you start anything, you need to determine the water needs of the plants and trees you're looking to address. This is necessary to ensure you're choosing the best type of emitter for each plant or zone, especially when it comes to vegetable gardens. Small moringa trees and seedlings require about 4 ml a day to sprout and reach their first leaf development. Then, once wood is forming, they will require about 60 ml of water a day each. Once the tree is producing many branches and has flowers and drumsticks, it will require 1 L per day. Map out your system, making sure to include measurements, emitter locations, and flow rates, and other information you'll need during installation or even purchasing. Pay extra close attention to tubing and emitter sizes. Mind your flow rates. In addition to knowing how much water a plant needs, you need to consider the type of soil it's found in. Too fast a flow in the wrong soil can lead to runoff and waste, while a slow flow in quick draining soils may not provide enough water. Tubing has limits. Keep in mind that each run of tubing needs to be kept under a certain length and below a certain flow rate, or else you're likely to experience problems with pressure loss and uneven watering. When it comes to 1-2 tubing, there's something called the 200-200 rule. Keep each individual run of 1-2 tubing under 200 feet from the water source, and make sure that the combined flow rates of all the emitters on that run don't exceed 200 GPH. For 3-4 tubing, follow the 480-480 rule. 0414 tubing, the shorter the run, the better. Although there is a 30-30 rule, 30-foot max length, 30 GPH max flow rate, others recommend keeping runs of 1/4 tubing under 20 feet. Keeping these runs short should be easy, since 1/4 tubing typically comes off the main 1/2 line only far enough to reach nearby plants or trees. You may be able to get away with longer runs of either size, provided the number and or flow rates of the emitters on it are below the 200 GPH for 1/2 or 30 GPH for 1/4 maximums. For example, a 275-foot run of 1/2 tubing with emitters that add up to 75 GPH should perform fine. As a rule, keep the combined length of your main and lateral lines, 1.2 and 1.4, under 400 feet from the water supply. If this doesn't cover your whole garden or yard, consider installing multiple zones by either splitting the supply from the outdoor faucet, provided you have a 40+ PSI supply, installing at multiple faucets, or using a multi-zone timer. Multiple irrigation zones allow you to water a greater area without the risk of pressure loss or other problems. Zoning can be accomplished in several ways depending on the situation and your garden's needs. As mentioned above, the simplest way to create multiple zones is by splitting the output from an outdoor faucet using a Y fitting, commonly referred to as a garden hose splitter. Most municipal water supplies have a pressure of 40 PSI or above, so you shouldn't encounter any problems supplying two zones at 20 PSI each. Don't forget pressure regulators at each hose connection if you'll be running them simultaneously. A single regulator at the inlet will suffice for zones run one at a time. Another simple method is to use inline valves to create a manually controlled zoning system. A valve is installed before each zone, allowing you to manually control which area gets water. You'll need a good memory and a lot of dedication for this method to work, but it does accomplish the task. Multi-zone manifolds and timers are the most advanced and powerful option. These devices utilize solenoid valves, electronically controlled valves that close themselves to automatically control which valves are open at a given time. Simply program the unit, connect it to the supply and your drip system hoses, and let nature take care of the rest. One creative alternative to these traditional zoning method is to use quick connect fittings to manually connect and disconnect a given drip line. Multiple hoses feeding different zones can be switched out at the same outdoor faucet within seconds and without tightening. Just don't forget where you're watering.
Installation tips.
Installation itself is usually a straightforward affair. Tubing is laid out next to the plants, a hole punch is used to pierce it, and an emitter is placed in the hole. In most applications, 1/2 tubing is used to supply individual 1/4 feeder lines, but many will stick emitters directly into 1/2 tubing. Stakes are used to keep the tubing in place and close to the ground. A typical drip system for a home garden will have the following layout at the water source, usually an outdoor faucet hose bib, sometimes a PVC supply pipe. This is often referred to as the faucet assembly. A pressure regulator connected to the faucet hose, bib, or supply pipe, followed by a filter. Straight inline filters can be directly connected to the regulator. Y-style filters will need a female hose adapter. A vacuum breaker is then connected to the filter, followed by a compression adapter, which will allow you to go from the male threads of the vacuum breaker outlet to a compression end which accepts 1/2 drip tubing. Most hard poly tubing can be buried, but doing so runs the risk of clogging or collapsing the line. Look for UV-resistant tubing that will not break down when exposed and covered only with layer of mulch. Afraid of putting an emitter in the wrong spot? Thanks to special plugs, you don't need to be. Beyond remedying hole punch mistakes, plugs allow you to utilize old tubing in good condition for new layouts. Simply replace unnecessary emitters with plugs and make new holes. Another plug that comes in handy is an end plug, which is installed at the end of a line. This allows water to still flow through but prevents bugs from getting in and clogging or damaging the line. Oh, pro tip. For new installations, we recommend leaving the end of the tubing uncapped and flushing the system before installing emitters and caps. This will help you find any leaks and flush out any sediment. If you live in an area with freezing winters, your drip irrigation system will need to be winterized, something you're probably, hopefully, used to. 1. Disconnect the faucet assembly, regulator, filter, vacuum breaker, compression adapter, and store it indoors. Remove batteries from timers. 2. Open any valves in the system and remove end caps to drain any water remaining in the tubing. When possible, lift the line slightly to facilitate draining. Once drained, close cap off both ends of the line. 3. Buried lines should be fine, but if your tubing is above ground, you may want to roll it up and bring it indoors to avoid freezing damage.